what we do is just we will observe how these characteristics or the wave phenomena will be varied for different medium. Here till now we discussed about a lossy dielectric medium. Since it is a lossy dielectric medium, that can be treated as a general one. Now I will modify all the parameters what we derived for lossless dielectric medium. So what is lossless dielectric medium? Clearly observe the characteristics. A lossless dielectric medium will have zero conductivity. Since it is lossless dielectric, conductivity is 0. And epsilon is equals to epsilon naught epsilon r. Mu is equals to mu naught mu r. So these are the characteristics of our a lossless dielectric medium. Now what are the parameters we are supposed to observe while deriving the equations? We gone through our propagation constant gamma. Gamma is equals to under root j omega mu multiplied with sigma plus j omega epsilon. This is the quantity that what we have. After that one we gone through phase velocity. That what is the phase velocity? Phase velocity is equals to just it is omega by beta. And after that let us take our intrinsic impedance. Intrinsic impedance are the characteristic impedance of the medium eta. Eta is equals to under root j omega mu divided by sigma plus j omega epsilon. Now we are going to define another parameter also, that is nothing but wavelength. So what is wavelength? A very simple concept. Whenever the wave is taken, let us take this is a wave that what we have. The distance between two crests, simply that will be treated as wavelength. So in short, that as per definition what we have to say is, it is the distance travelled by the wave. It is the distance, it is not time domain. It is the distance travelled by the wave to attain 2 pi radians phase shift. Obviously from crest to crest it is taking the 2 pi radian phase shift, right? So the phase constant now come into the picture, that is beta. How much phase shift was attained? 2 pi phase shift was attained. For which distance? For lambda distance. Simply the phase constant, the phase shift taken per length, so radian per meter. The phase shift attained for this particular distance is 2 pi, per distance is lambda. Therefore clearly the wavelength now can be written as, in terms of beta, it is 2 pi by beta. And what are the units of lambda? Meters. And so sometimes it is millimeters or nanometer, whatever it may be. That also we will consider here, that lambda wavelength is equals to 2 pi by beta. So whenever we got this beta from this, just substitute here to get the wavelength. And the last parameter what we are supposed to consider is loss tangent, that is tan theta loss, which is equals to sigma by omega epsilon. These are the general characteristics of our wave. Now we have to modify these general characteristics in according with the conditions what we have for lossless dielectric. So what I do is just I will modify one by one. Now come to the propagation constant. The propagation constant for the lossless dielectric, gamma is equals to under root j omega mu. Mu is equals to mu naught mu r, as it is I can write. Now sigma is 0 plus j omega epsilon. Epsilon is equals to epsilon naught epsilon r. Now simply which is equals to under root j multiplied with j, it is minus omega square mu epsilon. Minus omega square mu epsilon is j, is the minus 1 is j omega under root mu epsilon. This is a simple solution. Now clearly observe here, gamma is equals to j omega under root mu epsilon. Here I can add a 0 plus, that is a real term. Now compare this one with the original form of our gamma. What is the actual form of our gamma? Alpha plus j beta. Since it is alpha plus j beta, just the real term alpha becomes 0 and beta becomes omega under root mu epsilon. Alpha equals to 0 corresponds to what? And beta is equals to omega under root mu epsilon. And among these two, alpha is equals to 0 is important. What is alpha equals to 0? Alpha is nothing but the attenuation factor. Attenuation factor is 0. Attenuation factor is 0 means there is no attenuation. If there is no attenuation, no loss. That's why it is said to be the lossless dielectric. Clearly remember, for lossless dielectric always alpha is equals to 0. Not only for lossless dielectric, for any lossless medium alpha is equals to 0. If you remember this, the same is applicable in our transmission lines also, where we say that it is a lossless transmission line, alpha is equals to 0. And if you remember this particular equation, beta is equals to omega under root mu epsilon, a similar quantity will appear in our transmission lines also. For some time, just remember this equation, that gamma alpha is equals to 0, beta is equals to omega under root mu epsilon. And the second quantity what we have is a phase velocity. From this, the phase velocity can be obtained. Phase velocity is equals to omega by beta, just beta is this, omega by omega under root mu epsilon, which is equals to just 1 by under root mu epsilon. So purely depend upon the value of mu and epsilon, the phase velocity will be varied. That is our second quantity. And the third quantity what we have is intrinsic impedance or the characteristic impedance. So eta is equals to under root j omega mu remains as it is for us, that j omega mu divided by, now sigma is equals to 0. Since sigma is equals to 0, in the denominator what we have is just j omega epsilon. So the result is just under root mu by epsilon, nothing more than that. So if you take mu and epsilon substitute here, what we get is the characteristic impedance of that particular lossless dielectric medium. Next, wavelength. 2 pi by, what is beta? From this obtain beta, omega under root mu epsilon, omega under root mu epsilon, which is equals to, this can be written as 2 pi f by omega f. If you add f and f on the numerator and denominator, 2 pi f can be omega, omega will be cancelled. So lambda is equals to 1 by f root mu epsilon. That is nothing but our wavelength. And the last parameter what we are supposed to observe is loss tangent. Since sigma is equals to 0, what about the loss tangent? Loss tangent is tan theta loss, which is equals to 0. If the loss tangent value is 0, we can say that it is a lossless medium. If it is very less, simply we can say that it is a low loss medium. So these are the characteristics of our lossless dielectric medium. For the lossless dielectric medium, attenuation factor is 0. We may have some phase, some phase constant. Phase velocity is equals to 1 by under root mu epsilon. Eta is equals to under root mu by epsilon. And loss is simply 0. Now we have to go for the similar analysis for another medium also. That what we do is we will try to take free space. For the free space, we will observe what are these parameters. Now that is very important to remember also. So in most of the examinations, directly the characteristics for free space will be asked. So what we do is we will try to modify these equations, or we will try to get the solutions for these equations for free space. How the characteristics of free space were described? Clearly, the free space has conductivity sigma is equals to 0, epsilon is equals to epsilon naught, and mu is equals to mu naught. The analysis is very similar to previous one. Just we have to replace these quantities here. Then what is our gamma? Initially we will get gamma. Gamma is equals to under root j omega instead of mu, write down mu naught, into sigma is 0, just it is j omega epsilon naught. So j omega mu naught into j omega epsilon naught. So which is equals to, similar to previous one, j omega under root mu naught epsilon naught. So clearly observe that particular quantity. That quantity is only imaginary quantity, there is no real term in this one. Therefore we can write alpha is equals to 0. Since there is no real term, alpha equals to 0. In an ideal condition, the wave will go for an infinite distance without attenuation in free space. Remember that point. And what is beta? Beta is equals to omega under root mu naught epsilon naught. Here this mu naught and epsilon naught both are constants. So if you substitute that mu naught and epsilon naught, and if you calculate that particular term, that is equals to 1 by c. That's nothing but the velocity of light. So this beta can be written as, for free space exclusively, omega by c, where c is velocity of light. That a very simple point, you need to remember that. That omega under root mu naught epsilon naught is the equation after substitution of these two, what we get is 1 by c. And the second quantity what we have is phase velocity. That phase velocity is equals to omega by beta, which is equals to, if you take this one, omega by, what is beta here? Omega under root mu naught into epsilon naught, which is equals to just 1 by under root mu naught epsilon naught. As we said, this 1 by under root mu naught epsilon naught is velocity of light, simply it is equals to c. So what you can understand, in free space, the phase velocity is equals to the light velocity. The phase variation of the wave in the free space will be taken with the light velocity. Directly see, that's a constant what you have to remember. And the third one, intrinsic impedance of the free space, which is equals to under root j omega mu naught. Directly I am writing here, under root j omega mu naught divided by sigma is 0, j omega epsilon naught, which is equals to under root mu naught by epsilon naught. If you substitute that mu naught and epsilon naught values, you will get a constant. That constant is simply equals to 120 pi or approximately equals to 377 ohms. So this is a very important constant we have to remember. The characteristic impedance of the free space what we have is simply 120 pi or 377 ohms, which is equals to under root mu naught by epsilon naught. The same way, go for the wavelength. Wavelength is equals to lambda is equals to 2 pi by beta. What is 2 pi by beta? Beta is equals to omega under root mu naught epsilon naught, which is equals to, that's what I am writing is here, 2 pi f by beta f, which is equals to 2 pi f divided by, instead of beta I can write this omega f under root epsilon naught mu naught, right? 2 pi f is omega, omega will be cancelled, 1 by under root mu naught epsilon naught is c. So simply this can be written as c by f. That's why clearly always remember that the wavelength in free space is equals to velocity of light divided by the frequency. A very simple relation. This is very much known to us, right? In the same way for dielectrics also, wavelength is equals to velocity by frequency. That's what we get. If you go for that equation and if you manipulate that, what we get is lambda is equals to velocity divided by frequency. And the final one, loss tangent. The loss tangent is tan theta loss is equals to simply 0. Since sigma is equals to 0, what we get is 0. The loss tangent 0 means a very low loss, almost all 0 loss will be there. So these are the characteristics of our wave which is traveling in free space, right? This is our third medium that what we discuss, and the last medium what we are going to discuss is conducting medium. So if we are applying a wave to the conductor, and how these characteristics will be defined and what happens to that particular wave, we will discuss now. Now for the conducting medium, so how the conductor was described or the conducting medium was described. Clearly the sigma is approximately equals to infinite, that's a very high value, and epsilon is equals to epsilon naught, mu is equals to mu naught mu r. Now what we have to do is just we have to vary all those equations that what we have, but here the important quantities are just alpha and beta. That what I do is I will take those alpha and beta, I will try to modify them, but don't go for the basic equation of gamma. If you take the basic equation of gamma, it may not be possible to get the solution. So what I do is I will take the equations of alpha and beta, that what we learned in our earlier. So alpha is equals to omega under root mu epsilon by 2 under root of 1 plus sigma by omega epsilon whole square minus 1. So this is the equation of alpha. Now we are taking alpha as approximately infinite. Infinite means very high value, right? For a conductor, sigma is very high value. Since sigma is very high, sigma by omega epsilon whole square is also very high. That when compared with this one, since it is very high value, this one can be neglected, right? Just neglect this particular one in this one. After that one, square root of this quantity what we have, that is sigma by omega epsilon whole square under square root. Then it becomes sigma by omega epsilon. Sigma by omega epsilon minus 1, that what we get. This one also can be neglected. So clearly remember we are neglecting the remaining terms because of its high value, highness. So very high value, that's why we are neglecting it. Then what is the equation for this? What we got? Mu epsilon by 2 multiplied with this term only, that is sigma by omega epsilon. So if you simplify this, so omega can be taken into the square root, then it is omega square, which is equals to omega square, epsilon will be cancelled, mu sigma by 2. Mu sigma by 2 omega, which is equals to under root of omega mu sigma by 2. That this is a simple quantity that what we have for our conductor, that alpha is existing. and this has a sigma in numerator. Sigma in numerator means it is a very very high value. For high conductivity, the attenuation is very very high. That which is equals to, if you further simplify this one, what we get is omega is equals to 2 pi f, that what we can write, right? So 2 pi f mu sigma divided by 2, which is equals to just it is pi f mu sigma. That the attenuation because of the conductor, when a wave is traveling through that particular conductor, is directly under root pi f mu sigma. Just you observe and analyze that particular equation. It is directly proportional to frequency. It is directly proportional to conductivity. That we can say that if the conductivity is more, the attenuation is more. If the frequency is also more, the attenuation is more. That's why simply remember a point. Whenever the high frequency signal is applied to a simple conductor, that will not allow that particular high frequency wave within that conductor. That particular wave will be attenuated immediately when it is traveling through the conductor. That what we discuss as a skin depth. Later we will discuss that one. Now come to the beta also. That what is the equation of beta? Beta is equals to a similar equation that what we have here. That under root of mu epsilon by 2 square root of 1 plus sigma by omega epsilon whole square. Here it is plus 1. This is for beta. Once again, the similar type of approximation will be taken here. Since sigma by omega epsilon is very very high value, this one can be neglected. After square root, this one also can be neglected. Then what we get is a similar term, which is equals to omega under root mu epsilon by 2 sigma by omega epsilon, which is equals to a same type of term can be observed here, which is equals to under root of pi f mu sigma. So here clearly for our conductor, the alpha and beta are same. That the remaining from this beta, remaining all terms can be obtained, right? So clearly compile this, that is alpha is equals to beta is equals to under root pi f mu sigma is the quantity that what we are supposed to remember. The remaining quantities you can derive, right? But here we are supposed to take another parameter called as skin depth. What is skin depth? How it is defined? How to derive the equation for that skin depth? It's a very simple concept. We are supposed to observe that one. Let us take a conductor or any material. So let us take this is the material that what we are considering, and we are applying wave to that particular material. So how much distance a wave is traveled to attain 36.7 or approximately 37% of its initial value is called as skin depth for that particular material. Once again, we are applying a wave that how much distance it is traveling to attain 37% of its initial value can be treated as skin depth. So here the initial value, let us take some A. After traveling some distance, what we are getting is only 36% of the A. That distance is called as skin depth. Now we are supposed to derive that skin depth for any material. As we discussed, what we are doing is we are applying a wave to a particular medium at the initial point, and we are observing how much distance it was traveling to attain 37. That's in short e power minus 1 times of the initial value. So just you take the basic amplitude parameter of the wave. What is the amplitude parameter of the wave? That is E naught plus e power minus alpha z. That is only the amplitude parameter of the wave. So what happens to this amplitude parameter after traveling a distance lambda? Let us take this is a delta, not lambda. This is a delta. Skin depth is delta. After traveling distance of delta, it is attaining e power minus 1 times of its initial value, right? What is the initial value for this one? Initial value means at z is equals to 0. The initial value is just E naught plus. That is the initial value. Now how much distance it is getting traveled? For distance delta. So just take the distance traveled signal as e power minus alpha into delta. This much distance it was traveled. After traveling that much distance, what is the value? E power minus 1 times of the initial value. Just observe here what I am doing, nothing more than that. I am taking the wave amplitude quantity, and from this amplitude quantity I am getting the initial value, that E naught plus is the initial value. Now this amplitude quantity was traveled for how much distance? Delta distance. That's why I replace this z with delta. E naught plus e power minus alpha z is the distance traveled by the wave. that is delta distance traveled by the wave. After traveling this distance, what is the quantity equals to? E power minus time 1 times of the initial value. Just compare them. If you compare them, what we get? Minus alpha delta is equals to minus 1, which corresponds to delta is equals to 1 by alpha. So here clearly the skin depth for any material is inverse to the attenuation factor. In general, what we have to say is, if it is traveling for more distance, no attenuation is there, very low attenuation is there. Observe here, for low attenuation, the skin depth is more, the wave can travel for more distance with less degradation. If that alpha is high, if the attenuation is more, then delta is very less. So if you observe that one in a simple way, for dielectrics, what is the value of alpha? If it is lossless dielectric, alpha is 0. Therefore, delta is approximately equals to infinite for lossless dielectric. Simply for lossless dielectric, approximately delta is infinite means the wave will travels for an infinite distance for very good strength. That's what we can say. And for free space, also it is infinite for free space, right? Since alpha is equals to 0, in free space the wave will travel for an infinite distance approximately without any loss or degradation. Now come to the conductor. So what is the delta value for conductor? Delta is equals to 1 by under root pi f mu sigma. This is the important equation you are supposed to remember, because some problems may given to calculate the skin depth. So by giving a frequency, conductivity and permeability of that particular medium. So this is the equation what you have to remember. Delta is equals to 1 by under root pi f mu sigma. That for high conductivity, this delta is very less. So if you substitute this conductivity and frequency some points here, what we get is the answer may be in some millimeters or micrometers. So whenever we are applying a signal to the conductor, an electromagnetic wave to the conductor, then it will travel for only a very few distance, that may be up to 1 centimeter or 2 centimeter. After that, it will be completely attenuated. This is the reason why we are not supposed to use our conductors for high frequency applications. Instead of taking a simple conductor, we will go for transmission lines or another waveguides. That this skin depth will play very important role in that particular aspect. So with this one, the basic concepts of our wave propagation, what is the wave equation for electric field, magnetic field, and what are different phenomena, the characteristics which are related to the wave will be all that are discussed, and this is a simple introduction of our waves.